Nothing is quiet in the way this opening silence is quiet. It is not the absence of sound, but the absence of any place where sound could exist. No space, no time, no before, no after. Just a stillness so complete, it feels impossible that anything could ever disturb it. And yet we stand here, billions of years later, trying to imagine a state that was never meant to be imagined. A state beyond emptiness, where even the idea of emptiness had not yet been born. Because this is the paradox that greets us. If nothing once existed, how did it ever fracture into something? How does a universe rise from a void that owns no laws, no spark, no canvas to paint itself upon? The mind resists the question. It should. Nothingness was never meant to feel comfortable. It was meant to unsettle, to stretch thought until it trembles. But that trembling is where curiosity lives, and where every great story begins. So we step closer to the edge of the impossible and ask the question that refuses to rest. What if nothingness was only the beginning? Before we can speak of nothing, we must first surrender the comforting illusion that we already understand it. Because the truth is simple and unsettling. We don't. We never have. The word nothing rolls easily off the tongue, used casually in daily life, as if it were a small empty box we could pick up, examine, then set aside. But the moment we try to hold it under the full weight of philosophy and physics, the box collapses, the idea dissolves, and suddenly we find ourselves staring not into an empty space, but into a problem that grows the closer we approach it. We say things like, "There was nothing before the universe," or "Imagine total emptiness," as if the mind could simply remove a few pieces of reality and be done. But to imagine nothingness, true nothingness, is to attempt the impossible. Because the mind has only ever known something. It was built inside a world of shapes, colors, sensations, and laws. Even when we close our eyes and picture darkness, that darkness is still something. It has a location. It has a presence. You exist in relation to it. And so the first illusion shatters. Nothingness is not darkness. It is not a void. It is not a vacuum waiting patiently to be filled. Take away the stars, and you still have space. Take away space, and you still have geometry. The potential for location. Take away geometry, and you still have mathematical truths that remain even if no universe exists to express them. Strip away everything the mind can name, and something remains. But why? Why does the concept of nothing refuse to obey us? Because nothing is not a bucket we empty. Nothing is a cliff we fall from and never reach the bottom. Philosophers understood this long before physics entered the scene. When they tried to define nothing, they discovered that every definition smuggles a something inside it. To say nothing exists assumes the existence of a state in which existence is absent. To say nothing is already gives nothing the status of being. Even the statement, "there is nothing," breaks under its own weight, because the phrase implicitly declares that there is a condition to be described. Language betrays us, thought betrays us, and perhaps reality betrays us too. So physicists stepped into this philosophical quicksand with their own tools, hoping to formalize the void. But the deeper they dug, the stranger the terrain became. In physics, nothing can mean many things, and none of them resemble absolute emptiness. The most familiar version is empty space, a region without matter. It sounds like a reasonable candidate for nothing, until you look closer. Empty space seethes with quantum activity, particles appearing and disappearing, energy fluctuations rippling through the vacuum. Space is not a stage, it is an actor. It has tension, curvature, personality. A quantum vacuum is not nothing. It is a boiling storm of possibility. So the physicists refine the definition again. Maybe nothing is the absence of particles and fields, a state stripped of all excitations, a universe with no contents. But even here, the vacuum is not truly empty. It has structure, equations that govern how fields behave, symmetries that dictate what can exist, conserved quantities that remain whether or not anything fills the void. Take away the universe's contents, and the universe still has rules. Take away the rules, and the universe still has mathematical frameworks in which rules could exist. Even a lawless void has geometry, unless geometry itself is erased. So the physicists pushed further. Could nothing be the absence of space and time themselves? No fields, no vacuum fluctuations, no geometry, no dimensionality, no potential for anything. But this version of nothing has a terrible flaw. The moment we remove space and time, we lose the ability to say that nothing is a state at all. A state requires time to exist in. A state requires space to be somewhere. Without space-time, nothing is not merely empty, it is undefined. And so another paradox forms. The deeper we strip the universe, the more impossible the concept becomes. Nothing cannot exist as a thing. It collapses the moment we try to describe it. Think of the universe as a vast tapestry. We keep removing threads, matter, energy, forces, space, time, logic, until our fingers grasp at a fabric that is no longer there. But the question remains, what are we holding at the end? Is it nothing? Or is it simply something we cannot comprehend? A framework beyond all known frameworks. A condition that refuses to fit inside human language. Because to declare nothing existed before the universe is to assign existence to non-existence. To claim the universe emerged from nothing is to grant creative power to a void that has no attributes. Imagine absolute emptiness is to imagine a concept we are not equipped to imagine. Yet here we are, trying, sometimes. The only way to understand nothing is to watch what happens when we try to remove everything, and fail, because something always remains. A shadow of structure, a hint of form, a whisper of potential. The universe is stingy with its emptiness. It gives us illusions of nothing, but never the real thing. This is why modern physics treats nothing, not as a blank page, but as a spectrum. At one end lies the classical vacuum, empty space with no particles. At the other end lies the philosophical abyss, the total absence of any framework whatsoever. Between them are quantum vacuums, false vacuums, virtual fields, symmetries, and pre-geometric states that may have birthed space-time itself. Each definition pulls us deeper into confusion, but not a frustrating confusion, a fertile one, because every version of nothing carries astonishing implications. If empty space is not nothing, then even the most desolate regions of the cosmos hide invisible storms of energy. If the quantum vacuum is not nothing, then the universe is built on fluctuations that never fully disappear. If the absence of space-time is not nothing, then reality may spring from structures more fundamental than time and space. And if absolute nothing cannot exist, then the universe never rose from it. But this raises a question more daring than the original one. If the universe did not emerge from nothing, then what did it emerge from? A primordial field? A timeless mathematical structure? A quantum foam preceding time? Something like nothing, but not quite nothing. These are not merely scientific questions. They are philosophical detonations. They unsettle the story we tell ourselves about beginnings. Because we like clean narratives. First there was nothing, then came the universe. But reality refuses such simplicity. It forces us to confront a truth we don't expect. That nothingness is not an absence but a puzzle, a mirror reflecting our assumptions back at us. To explore nothing is to explore the edges of our own cognition. The mind seeks solid ground, but this topic offers none. Instead, it offers a strange kind of beauty, a beauty that lives in uncertainty, a beauty that whispers that the universe is deeper than logic, stranger than intuition, more layered than any story we've ever known. And perhaps this is the real reason nothing fascinates us. Not because the void is empty, but because it is full of mysteries we cannot dissolve. We chase nothingness the way sailors once chased the horizon, always seeing it, never reaching it, knowing that if we could grasp it, we would grasp the impossible. Yet here is the quiet twist. Maybe the universe did not begin with a bang emerging from a void. Maybe the universe was never competing with nothingness. Maybe nothingness is not a rival to existence, but a lens through which existence reveals its most profound secrets. Because if nothing is impossible, then something is inevitable. If emptiness cannot be absolute, then structure lies hidden beneath it. And if the void cannot erase all frameworks, then reality has deeper roots than we ever imagined. So we return to the question, reshaped now by everything we've torn apart. We asked what existed before the universe. We assumed the answer might be nothing. But every attempt to define that nothing dissolved in our hands, not a failure, a revelation. If nothing cannot exist, then what was there before existence? Before the universe could be described, it had to become something describable. And that threshold, the razor-thin boundary between absolute unknowability and the first flickers of physical law, lies in a place so small, so violently compressed, that the human imagination can only circle it like a distant star. We call it blank time. 10:43 seconds after the moment creation became possible. Not a moment, not a sliver, but the smallest unit of time our physics can meaningfully speak about. To go earlier is to plunge into a region where the very tools of understanding lose their shape, where the equations buckle, where even the concept of before may have no anchor. If Act 1 was the unraveling of nothingness, this is the trembling birth of almost something, a realm where the void phrase flickers and folds into possibility. Imagine a place where temperature is not merely high but so intense that the word temperature barely applies, where heat is not a measure of agitation but a storm of pure instability tearing through a fabric not yet fully formed. At 10:43 seconds, the universe was so dense that to compress your entire world, every atom, every memory, every star you've ever seen, into a space smaller than a proton, would still not match this primordial pressure. Even metaphors fail here. Even imagination stalls, because nothing in the modern universe can replicate these conditions. The early universe was not a place. It was not a space filled with energy. It was the energy. It was the space. A single trembling identity flickering into coherence. Physicists describe this era as a quantum foam, a phrase that seems gentle, almost playful, until you understand what it tries to capture. Foam, because space-time did not flow smoothly like a calm river. Foam, because it boiled with fluctuations so wild that geometry itself rippled, tore, and stitched itself anew countless times per heartbeat. But even the word boiled simplifies it too much. This was not heat in water. This was possibility erupting into micro-universes and collapsing before they could even be born. A storm of baby realities, flashing into existence and vanishing again, like sparks from a friction no one yet understood. Nothing stable, nothing lasting, nothing that could be called our universe. Just a riot of attempts, failures, and phantom beginnings. In this primordial turbulence, particles did not exist as the discrete points we imagine today. They were smeared across probabilities, dissolved in uncertainty, humming between being and not being faster than any meaningful measure. Even time, if it can still be called time, did not tick forward. There was no pass, no sequence, no cause leading to effect. Instead, everything happened at once, and not at all. Physics says causality was not yet locked in. Events did not have to follow one another. They could coexist, contradict, and overlap in ways that our modern universe would never tolerate. Time itself was learning how to be linear, how to flow, like a river carving its first channel, hesitant, unstable, searching for direction. This is the razor edge where creation becomes possible. Not creation as a single explosion, but creation as the gradual emergence of order from an ocean of chaos. And to understand this emergence, we must accept a strange lesson. The universe did not begin with clarity. It began with confusion. It began with laws that had not yet agreed to become laws. Forces still braided together. Constants still fluid. Reality negotiating the terms of its own existence. Imagine the universe as an orchestra, warming up. Not playing music yet, but making noise. Each instrument improvising, clashing, stumbling, waiting for the moment when a common rhythm emerges. At 10 to 43 seconds, the instruments were tuning, not playing. The cosmic symphony had not yet begun. And yet, within this roaring uncertainty was something extraordinary. A tendency toward coherence, as if the chaos itself remembered something, as if the universe was built with an impulse not to remain wild forever. Physicists call this impulse symmetry breaking, the moment when the forces that were once united begin to differentiate. Gravity separates first, slipping out of the unified storm like a shadow stepping away from a light source. It becomes the first force to stand on its own. Suddenly, a rule exists where there was no rule. A direction exists where previously direction had no meaning. And this tiny deviation, so small it seems almost trivial, is the first whisper of the universe we know today. But this separation does not happen gently. When gravity peels away from the unified field, it sends a tremor through the quantum foam. A shudder, a structural shift, a change in the way space-time curls and twists. Imagine a sheet shaken at one corner. Waves race outward. Patterns emerge. The early universe reacted the same way. The moment gravity distinguished itself, everything else had to reorganize around that distinction. Geometry responded. Energy condensed. Fluctuations sharpened, focusing into more structured forms. Chaos took one step closer to order. A step so small it lasts only 10:43 seconds, yet so profound that it sets the trajectory of the entire cosmos. Beyond this threshold, the universe is still unrecognizable, still blisteringly hot, still unstable, still flickering between identities. But something fundamental has changed. Physics finally has a foothold. The universe is no longer a place without laws. It is now a place with laws struggling to declare themselves. With gravity anchoring the stage, other forces prepare to differentiate. Electromagnetism, the strong nuclear force, the weak nuclear force, all braided together, waiting for their turn to split apart and shape the future. Each division is a cosmic milestone. Each separation carves more structure out of the storm. Reality is sculpting itself, one force at a time. Temperature, in this era, is beyond anything the modern mind can appreciate. We describe it in terms of energy rather than degrees, because degrees become meaningless. At this scale, heat is not a measure of motion, but a measure of fundamental disruption. Everything is too energetic to stay still, too chaotic to settle. Particles cannot maintain identity. Space cannot maintain curvature. Time cannot maintain flow. And yet, incredibly, this chaos is fertile. It contains the seeds of everything: atoms, galaxies, consciousness, waiting for the moment when energy cools just enough for structure to emerge. Not calm, not stability, just slightly less impossible. Even causality, the simple idea that one thing leads to another, is still finding its footing. At the quantum scale of the Planck epoch, fluctuations can produce outcomes without causes, or causes without predictable outcomes. A universe like this cannot support permanence. It cannot support memory. It cannot support the continuity that makes existence feel real. And that is why this era is so brief. Nature cannot linger in a state where nothing can persist. The universe must race forward, expanding, cooling, differentiating, because that is the only path toward stability. Toward longevity, toward evolution, time must learn to flow. And flow it does, explosively. As expansion begins to accelerate, the quantum foam stretches. Fluctuations lengthen. Temporary configurations become longer-lived. For the first time, the universe becomes a place where events can be meaningfully separated, where a before can influence an after. This is the quiet birth of proto-time, the earliest version of the temporal river we now travel through. Not smooth, not steady, but flowing enough that physics can begin to predict, to describe, to understand. The cosmos is still wild, furious, radiant, unimaginable, but it is no longer unknowable. It is becoming a universe. In this briefest sliver of existence, the foundations of everything are laid. The constants that will shape chemistry, the forces that will govern stars, the values that will determine whether galaxies can form at all. These are not chosen later. They crystallize here, at the edge of physics. A moment when reality is soft enough to be molded, but firm enough to retain its shape once cooled. If they crystallized differently, nothing, including you, would exist. This is the moment creation becomes possible not through magic, but through mathematics. Not through intention, but through consistency. The universe is learning to hold itself together. And so the Planck epoch fades. Not with a bang, but with a transition so subtle that we cannot observe it directly. Only its consequences remain. The universe has cooled just enough. The chaos has slowed just enough. The laws have stabilized just enough. And with those small shifts, reality takes its first confident step forward. A step toward particles, toward forces, toward structure, toward everything that will one day become stars and planets, and the minds that wonder about them. The story moves from the unseeable to the almost seeable, from pure possibility to the first hints of form. And then, a moment arrived that changed everything. Creation did not begin with sound. It began with silence pushed beyond its ability to remain silent. A silence stretched, strained, and then, without warning, unfolded. Not in an explosion of fire and noise, but in something far stranger, an eruption of space itself. Inflation was not a bang. It was acceleration. It was emptiness learning how to expand. It was nothing discovering it could become more than nothing. And it happened so quickly, so violently, so completely, that the human mind can only reconstruct it through metaphors that all fall short. Because how do you describe a moment when space didn't merely grow, but doubled and doubled again in the blink of a blink of a blink? A moment when the universe didn't expand into anything. It expanded as everything. In the aftermath of the Planck era, the universe was unstable, restless, overflowing with energy that had no place to settle. Imagine a field stretched too tightly, trembling, desperate to release its tension. Physicists call this the inflaton field, a strange entity that carried within it the potential for sudden and catastrophic expansion. Its energy density was enormous, far beyond anything the modern cosmos contains, and yet it remained almost perfectly uniform, like a bowstring drawn back to its maximum limit. A bowstring that, once released, would unleash a transformation so complete that nothing in the universe would ever be the same again. What happened next defies ordinary language. Inflation began, not with sparks, not with shattering, but with the sudden collapse of the inflaton stability, a collapse that acted like a trigger. Space didn't just grow, it multiplied. Every tiny region expanded so rapidly that the distance between 2 points doubled at a rate that eclipsed the speed of light. Not because anything traveled faster than light, but because space itself outran any signal trying to cross it. This distinction is crucial. Nothing violated physics. Physics simply changed scale, embracing an intensity it had never displayed before. In much the same way a seed becomes a forest, inflation turned a quantum speck into a cosmic expanse. But unlike a forest, it did so almost instantly. To grasp the violence of this period, imagine a sheet of fabric stretched tight, with tiny creases barely visible on its surface. Now imagine pulling that fabric so quickly and with such force that those creases expand into mountain ranges. This was inflation's greatest magic. Tiny quantum fluctuations, microscopic variations in energy, were pulled apart until they became macroscopic. Patterns too small to notice were inflated into the scaffolding of galaxies. Ripples in the vacuum became the cosmic web. Probability storms became the shape of everything that would follow. Inflation did not just stretch the universe, it gave it structure. It took randomness and sculpted it into destiny. And all of this happened in less time than it takes for light to travel across a proton. Less time than the smallest fraction the human mind can envision. Inflation lasted for approximately 10 to 32 seconds. But in that instant, the universe grew from smaller than a subatomic particle to the size of a grapefruit, then to a planet, then to a star system. Some models suggest even larger, expanding to a scale comparable to entire galaxies in a heartbeat. What was once impossibly small became inconceivably vast, and in that brief moment, the seeds of every star, every planet, every living thing were planted, not by choice or design, but by the natural consequences of quantum mechanics amplified to cosmic proportions. This is the paradox at the heart of creation. Nothing exploded without exploding. No fire, no smoke, no shockwave. Just the silent rush of space unfolding far faster than any ordinary physical process. A transformation so rapid that if consciousness had existed to witness it, it would have seen nothing at all. Inflation outran observation. It outran itself. It was speed without motion, expansion without explosion, energy without form. It was the quiet blooming of a reality that had been waiting to take shape. Yet even in its violence, inflation was delicate. So much depended on the tiny variations in the inflaton field. Variations so small that they resembled whispers in a hurricane. If the field had been too smooth, the universe would be perfectly uniform. No galaxies, no stars, no atoms clumping together. A featureless canvas incapable of complexity. If it had been too chaotic, matter would collapse into black holes or disperse so widely that structure could never form. But the universe emerged in a narrow, improbable middle ground. Just enough irregularity to form cosmic architecture. Just enough smoothness for gravity to weave it together. Inflation carved this balance with astonishing precision. Consider what that means. The patterns imprinted on the cosmic microwave background, the faint afterglow of ancient heat, are fingerprints of quantum noise, stretched across trillions of miles. Every ridge, every valley, every cluster of galaxies is an echo of an uncertainty principle magnified across the expanding cosmos. The deepest structures of reality are fossils of randomness. The universe did not emerge from a blueprint. It emerged from fluctuations so small that they should have vanished without consequence. Instead, they became the constellations. They became the Milky Way. They became the elements forged in stars. They became us. Inflation also performed another miracle. It flattened the universe. Any initial curvature was stretched so drastically that the cosmos became indistinguishable from perfectly flat space. This flatness is not a trivial detail. It determines how gravity behaves on the larger scales, how galaxies drift, how the cosmos evolves. Without inflation, the universe would likely be curved, chaotic, unstable. But because inflation pushed every point away from every other point, it smoothed out irregularities, ironing the cosmos into a vast, even sheet. A sheet so perfectly balanced that its geometry remains on the knife edge between infinite expansion and gravitational collapse. Without inflation, the universe would not only look different, it might not exist at all. And yet inflation's power was not limitless. It came to an end, not with a sudden stop, but with a gradual slide. As the inflaton field rolled downward into a more stable configuration, the expansion slowed. Space still grew, but no longer exponentially. Time regained its rhythm. Energy condensed into particles. Forces differentiated. The universe cooled enough for the next chapter to unfold. And with inflation's end came a release of energy so enormous that it filled the cosmos with radiation, a moment known as reheating. This is the true beginning of the hot Big Bang. Not the origin of expansion, but the heating of a universe that had already expanded beyond comprehension. It is here that creation becomes recognizable. Particles swarm, photons scatter, Forces take their final forms. Gravity shapes primordial density fluctuations into the seeds of future galaxies. The universe becomes dynamic, energetic, full of motion. Inflation has ended, but its fingerprints remain everywhere, etched into the distribution of matter, into the horizon beyond which we cannot see, into the very geometry of the cosmos. And there is one more twist. Inflation may not have happened only once. Some theories suggest that inflation is eternal, a process that occurs repeatedly across a larger multiverse. In this view, our universe is just one bubble in an ocean of expanding space, one region where the inflaton field decayed in just the right way, while other regions continue inflating endlessly. If this is true, then inflation did more than shape our universe. It gave birth to countless others, each with different laws and constants. But even if we never confirm this multiverse, the concept reveals inflation's staggering implication. It is not merely a moment in time, but a mechanism for generating entire realities, a cosmic engine that may never truly stop. Returning to the simplicity of our own universe, we find ourselves marveling at the elegance of inflation. It solves puzzles that once seemed insurmountable. It explains the universe's flatness, uniformity, and structure. It provides a bridge from quantum chaos to cosmic order. And yet, at its heart, inflation is still a mystery. What triggered it? What ended it? What field powered it? Why did it produce just the right amount of irregularity? These questions linger, echoing through the silence inflation left behind. We understand the consequences, but the cause remains elusive. A reminder that the universe began with answers we can measure, but questions we cannot yet articulate. And so, the story accelerates with inflation, then slows as the cosmos stabilizes. The violent unfolding gives way to gentler processes: cooling, nucleosynthesis, the gradual dance of gravity. But inflation remains the moment when the universe's destiny was written in patterns too large and too subtle to see without stepping outside ourselves. It was the instant when the cosmos leapt from unimaginable smallness to overwhelming vastness. It was the brushstroke that painted structure onto the void. Then, almost as suddenly as it began, the storm faded, space relaxed, energy diffused. The universe exhaled, and in that exhale, creation became calm enough for the next transformations to take root. Stars would one day form, galaxies would spiral, life would arise, consciousness would wander. But all of that was still far in the future. For now, the universe rested, not in peace, but in possibility. From the storm, order began to whisper into existence. In the wake of inflation's violent unfolding, the universe found itself vast, hot, and overflowing with raw energy. A storm had stretched the fabric of reality to scales unimaginable. But now a new story began, one ruled not by expansion alone, but by cooling. And cooling, though gentle, is transformative. As the universe expanded, its temperature fell, and in that falling temperature, possibility took its first stable breath. Chaos softened. Energy slowed its frantic dance. What had been a blinding, unstructured sea of radiation began, ever so slightly, to calm. The universe was still young, far younger than a blink, but already its identity was shifting. It was no longer only a storm. It was a place where order could begin to emerge. The first great shift was baryogenesis, a moment both subtle and decisive. At these early times, the universe produced matter and antimatter in equal amounts. siblings born from the same energetic womb. For every particle of matter, there was a mirror particle of antimatter, identical in mass, opposite in charge. And when these pairs met, they annihilated into pure energy. By all expectations, matter and antimatter should have destroyed each other completely, leaving behind a cosmos of radiation and nothing more. But the universe is not a slave to expectation. Something about the symmetry broke. Matter gained the slightest, almost imperceptible advantage. For every billion antimatter particles, there were 1,000,000,001 particles of matter. A tiny imbalance, so small it feels like a rounding error. Yet it was this infinitesimal tilt, this cosmic whisper of more, that allowed everything that exists today to survive. Without that asymmetry, there would be no atoms, no stars, no galaxies, no life. The universe would be a graveyard of light with nothing to shine upon. But because symmetry broke, matter remained, and the story continued. Why did matter win? Physicists still search for a full answer. Perhaps new particles played a role. Perhaps the laws themselves were never perfectly symmetrical. Perhaps quantum fluctuations nudged the scales. Whatever the cause, that imbalance is the reason anything survives long enough to wonder about its own survival. Creation depends on imperfection. And in this moment, reality embraced just enough imperfection to ensure its future. As baryogenesis unfolded, another transformation was underway. The forces that govern reality were beginning to separate. In the earliest instance, all forces were woven together in a single, unified identity. But as temperatures dropped, unity fractured. Gravity had broken away first in the Planck epoch. Now the strong nuclear force began to distinguish itself, asserting its power within the subatomic realm. Soon after, the electroweak force, the ancestor of both electromagnetism and the weak nuclear interaction, prepared to split as well. With each separation came structure. With each distinction came clarity. The universe was no longer a place of formless energy. It was becoming rule-governed, predictable, consistent. A place where consequences followed causes. A place where laws would remain true for billions of years. It was during the electroweak phase transition that another profound shift occurred. The Higgs field, once drifting without influence, snapped into its true form. Like a fog suddenly condensing into dew, the Higgs field settled across the universe, permeating all of space. And as it did, particles that had once raced through the early cosmos without resistance began to feel a drag. A slow, subtle interaction that gave them mass. Before this, mass had no meaning. Particles moved as pure energy, indistinguishable in their weightlessness, but the activation of the Higgs field changed everything. It allowed certain particles to slow, to gain inertia, to become something other than light. The universe was learning to differentiate between the weightless and the weighted, between radiation and matter. Mass is structure. Mass is stability. Mass is the anchor that allows gravity to sculpt the future. Without the Higgs field, no particle would ever settle down long enough to build an atom. The cosmos would remain a blur of light, beautiful but barren. As cooling continued, quarks, the building blocks of matter, finally slowed enough to form bonds. They clustered into protons and neutrons, held together by the strong nuclear force, which now operated with the precision needed to maintain stability. These protons and neutrons were the first durable constituents of matter, capable of surviving the extreme conditions of the early universe. But they did not yet form atoms. The cosmos was still too hot, still too dense, still too full of free-flying particles colliding with unimaginable force. Imagine a room filled with sparks, so many, so bright, so chaotic, that no spark can remain near another long enough to form a flame. That was the early universe, a storm of energy so intense that matter could barely hold itself together. And yet, it did, slowly, stubbornly. With each passing moment, cooling made the improbable possible. During this era, the universe glowed with a harsh, radiant heat. Light so energetic it barely resembled the photons that reach our eyes today. The cosmos was a furnace, but a furnace that was losing its fire. And as the temperature fell below 1 trillion degrees, a new clarity entered the scene. The strong force held protons and neutrons tightly. The weak force allowed them to transform into each other. The electromagnetic force ensured that charged particles danced in predictable patterns. Gravity tugged softly but steadily, preparing for its ancient role of assembly. The laws were settling, the stage was stabilizing, physics was becoming physics. But even as protons and neutrons formed, a deeper contest raged beneath the surface. For every particle, an anti-particle still lurked, threatening annihilation. Matter was abundant, but danger was everywhere. Photons cracked through space like lightning, slamming into particles with enough energy to tear them apart. The early universe was not a peaceful nursery. It was a battlefield, violent, radiant, filled with collisions that reshaped the content of reality each moment. And yet cooling worked its quiet magic. With each fraction of a second, fewer interactions had the raw power to undo creation. The universe was still chaotic, but the chaos had limits. The furnace was dimming. Order was rising. As the temperature continued to drop, the electroweak force completed its separation, splitting into electromagnetism and the weak nuclear force. Two distinct personalities emerged from one unified ancestor. Electromagnetism became the architect of chemistry, the sculptor of atoms, the force that would one day carry light through the empty darkness between stars. The weak force became the quiet regulator of nuclear decay, determining how elements transform, how stars burn, how energy escapes from deep places. Each force took on a role that would persist across cosmic history. The universe was no longer improvising. It was rehearsing the physics that would shape everything that followed. By the time the universe reached a few minutes old, temperatures had fallen enough for the next act of structure formation: nucleosynthesis. Protons and neutrons fused to form the first atomic nuclei, primarily hydrogen and helium, along with traces of lithium and beryllium. These were not yet atoms, because electrons were still too energetic to bind. But the nuclei that formed in this era would remain stable for billions of years. They are the ancestors of all elements, the seeds from which the periodic table eventually grew. Simplicity came first, complexity would follow. It is easy to forget how delicate these processes were. If the strong force was slightly weaker, nucleosynthesis would fail, and the universe would contain nothing but hydrogen. If it was slightly stronger, nearly all hydrogen would fuse immediately into heavier elements, leaving no fuel for stars. If the electromagnetic force were different, atoms could not form. If the weak force behaved differently, stars would not burn in steady fusion. Every law that crystallized in this era carried consequences unimaginably far into the future. Even the tiniest deviations could have rendered the cosmos sterile. But the laws did not deviate. They settled into a balance so precise that entire galaxies could someday take shape. Cooling brought clarity not just to particles, but to space itself. Regions of slightly higher density gained the faintest gravitational advantage, pulling matter inward. These were minuscule variations, fractions of fractions imprinted by inflation. But they were enough. Gravity amplified them, gently at first, then with greater resolve. In time, they would become galaxies, clusters, and superclusters. But for now, they were merely whispers of shape, hints of a cosmic architecture still unimaginably far from completion. As the universe moved from its first seconds into its first minutes, a profound calm settled in. The violence of inflation was behind it. The frenzy of particle creation and annihilation was fading. The laws were aligned, the symmetries were broken, the fields were set. Matter existed. Radiation filled every corner. Gravity began its long work of sculpting. And though the cosmos was still hot, still bright, still energetic beyond comprehension, for the first time it behaved like a universe, predictable, coherent, lawful. Somethingness had taken root. The early fire was not gone, but it no longer raged uncontrollably. It flowed, it obeyed, it prepared, and in the quieting glow of this newborn clarity, the future was written in the simplest of elements, waiting patiently for stars to ignite and bring complexity to life. With the laws set, the cosmos prepared its next act. Darkness ruled the young universe far longer than light ever has. After the first furious minutes of creation, after nuclei formed and radiation blazed through the expanding cosmos, the universe entered a long, patient night. Atoms had not yet taken shape. Photons scattered endlessly, unable to travel far without crashing into freeze electrons. Space was hot, glowing, impenetrable. Light existed, but it could not move freely. It could not reveal. It could not illuminate. And so the cosmos waited. Expansion continued. Cooling continued. Slowly, almost reluctantly, electrons calmed enough to bind to nuclei. Hydrogen and helium, the simplest elements, finally became complete atoms. And in that transformation, the universe changed from opaque to transparent. For the first time, light could travel. But even then, though the fog had lifted, the universe remained dark. There were no stars yet, no galaxies, just an endless ocean of cooling hydrogen, drifting in an expanding night that stretched in every direction. But darkness does not last forever. Gravity remembers what light cannot yet reveal. It senses the faintest irregularities, tiny fluctuations left behind by inflation, and begins to pull. What seems impossibly smooth still contains small imperfections, and those imperfections become the seeds of structure. Clouds of hydrogen gather. They drift inward, they collide, they compress. It is a slow collapse, resisted at every moment by the heat within the cloud, by the pressure of gas pushing outward. Yet gravity persists. It tightens its grip. The clouds grow denser, hotter, more unstable. They are vast, light years across. But their fate is the same as a grain of dust falling into a flame. They ignite. The first stars were nothing like the stars we see today. They were giants, monsters of fusion, hundreds of times more massive than the sun, burning with a ferocity we can scarcely imagine. These were population 3 stars, the universe's first attempt at light. They formed quickly and lived briefly, their lives compressed into a few million years, an instant on cosmic scales. Their ignition ended the cosmic dark ages. In a universe that had known only darkness, the first spark appeared, then another, then countless others. The night began to glow. Imagine witnessing that moment. An endless darkness, stretching beyond sight, suddenly pierced by blue-white fireballs. Each star, a beacon announcing that complexity had begun. These stars heated their surroundings. Ionized gas sent shock waves rippling across the void. Their ultraviolet light carved cavities in the darkness. Their gravity drew material inward. They were both destroyers and creators, shaping the cosmos with their intense radiation. And their fusion furnaces built the universe's first heavy elements: carbon, nitrogen, oxygen, iron, the ingredients required for life, locked inside their cores. But these stars were too large to live long. Their deaths were cataclysmic. When they ran out of fuel, they collapsed inward and exploded outward in titanic supernova, the first great chemical enrichers of the universe. These supernovae were not mere endings. They were beginnings disguised as destruction. In their violent deaths, they scattered heavy elements across space, mixing them into the hydrogen seas. The universe was no longer chemically simple. It had new flavors, new possibilities. The building blocks of planets and future life drifted into the void, waiting for new stars to gather them. And each supernova sent out waves of energy that compressed nearby gas, triggering the formation of new stars. Light begot light, structure begot structure. The universe, once passive, now engaged in a self-amplifying cycle of creation. Regions of higher density collapsed into clusters. Clusters merged into protogalaxies. Gravity stitched them together into rotating disks and massive halos. The first galaxies took shape, messy, turbulent, unrefined, yet unmistakably alive. These early galaxies were crucibles of intense star formation, chaotic but creative, bursting with light that traveled freely across space, illuminating the cosmic web that slowly grew between them. This was the era when darkness began to lose its undivided reign. Light spread farther. Galaxies multiplied. Space itself became patterned, textured, intricate. What had started as tiny variations in density blossomed into a cosmic architecture spanning billions of light years. Filaments, voids, clusters. The skeleton of the universe emerged, carved by gravity, illuminated by starlight. And every flicker of that light carried information. Where stars formed, where they lived, where they died, how galaxies collided and merged. The universe was revealing itself one photon at a time. As galaxies matured, new generations of stars emerged. Smaller, longer-lived stars formed from gas, enriched by the deaths of the giants. These stars, unlike the first, could sustain themselves for billions of years, burning steadily, providing the stability necessary for planets to coalesce around them. Heavy elements, born in supernovae, assembled into dust grains clumped into rocks, rocks merged into planets. Solar systems took shape across the galaxies, each one a tiny drama of gravity and motion. Complexity deepened, diversity expanded, beauty multiplied. But the rise of complexity was not just physical, it was energetic. Light became more than illumination. It became a messenger. It carried the stories of distant galaxies across unimaginable distances. It allowed information to spread. It allowed structure to influence structure. Through light, the universe developed memory. A galaxy could feel the radiation of its neighbors. A star could heat a nebula light years away. A quasar could sculpt the evolution of an entire cosmic region. Light connected the cosmos, turning vastness into a network of influence. As time passed, galaxies grew into spirals, ellipticals, irregular jewels of stellar motion. They collided, cannibalized each other, merged into larger forms. These collisions were not quiet events. They were gravitational ballets, reshaping stars and gas, triggering new waves of star formation. In their chaos, beauty unfolded. The universe became a tapestry of glowing arcs, swirling arms, and luminous centers. And deep within many galaxies, supermassive black holes formed, anchoring their structures, devouring material, and releasing jets so powerful they could shut down or ignite star formation across entire galactic neighborhoods. Even darkness, compressed into singularity, became a source of cosmic artistry. All the while, the elements continued to evolve. Stars lived, burned, died, and seeded space with heavier elements: silicon, magnesium, sulfur, nickel, gold. Each generation of stars enriched the universe further, turning a once simple cosmic chemistry into a palette capable of painting worlds. Supernovae sowed iron for blood, calcium for bones, carbon for life, oxygen for breath. Every breath taken billions of years later would trace its lineage back to these ancient stars. Every heartbeat would echo a fusion furnace. Every world would bear the fingerprints of stellar death. The universe was not merely shining, it was building. And with each supernova, each nova, each quiet, stellar death, the cosmos grew increasingly capable of complexity. Nebulae formed, vast clouds of gas and dust illuminated by young hot stars. These nebulae glowed in blues, reds, greens, sculpted by radiation into pillars, arcs, and rivers of glowing matter. They were cosmic wombs, birthing new stars and new planets. Light did not only reveal these forms, it shaped them. Photons carved shadows. Heated gas set boundaries. Darkness was no longer simple absence. It was a canvas on which light performed its ancient dance. By the time the universe reached a few billion years old, the night sky, once empty, had become a cathedral of light. Stars filled the void. Galaxies spiraled across the darkness. The cosmic web interconnected everything, from the smallest cluster to the largest supercluster. And through this vast network, light traveled endlessly, carrying the universe's past into its present. Photons became storytellers of unimaginable journeys. They told of birth and death, of motion and stillness, of collisions and creations. Light became the language of the cosmos. But beneath the beauty lay something deeper: intention without intention. The universe did not choose to shine. It simply evolved into a state where shining became inevitable. Gravity carved structure, stars ignited, supernovae enriched, galaxies formed, and from this chain of natural consequences, complexity arose, unbidden, unstoppable, magnificent. What began as a dark, cooling cloud had become a universe capable of brilliance, and yet the story was far from over. Light was only the beginning, for with light came information, and information allowed the universe not only to exist, but to understand itself. Every photon that traveled, every wave that crossed the cosmic deep, carried clues about origins, about structure, about destiny. Light did more than illuminate. It connected the present to the past. It made discovery possible. The cosmos had awakened. It had learned to shine. It had grown intricate, rich, and full of potential. And somewhere in that vast canvas, of galaxies and stars, the conditions for life would one day emerge, shaped by the same processes that forged the first light from darkness. Complexity was not an accident. It was a continuation, a deepening, a promise inherent in the universe's earliest moments. Light carried information, and one day it would allow beings to witness their own origins. Long before consciousness opened its eyes, long before any creature wondered or feared or loved, the universe moved through its vast cycles without ever needing to understand them. Stars were born, stars died, galaxies collided, and not a single atom cared. Hydrogen did not know it was ancient. Carbon did not know it was forged in a furnace. Space did not know it was expanding. For billions upon billions of years, reality behaved with exquisite precision, yet remained entirely unaware of its own existence. It simply unfolded because unfolding was what it did. And then, somewhere in the quiet aftermath of countless stellar deaths, the story turned. Chemistry changed. Complexity deepened. And the universe took a step towards something unimaginable. The capacity to know, to understand how this happened. We must return to the stars, the great alchemists of existence. When the first massive stars died in supernova explosions, they cast into space the seeds of all future complexity. Carbon for life's backbone, nitrogen for genetic codes, oxygen for breath, phosphorus for cell membranes, iron for blood. These elements drifted through nebulae, mixing, cooling, waiting. Over generations of star formation and destruction, the cosmic pantry filled. Simpler molecules formed, then more complex ones. Dust grains coated with frozen chemicals gathered into disks around young stars. From these disks, planets emerged, some barren, some molten, some promising. Among them were worlds where conditions stabilized into narrow, improbable windows, not too hot, not too cold, with liquid water, protective atmospheres, and stable orbits. These worlds were rare, but they were enough. On at least one of them, ours, chemistry began to flirt with something deeper. Molecules interacted, linked, separated, reformed. Chains built upon chains, forming structures capable of copying themselves. It was not yet life, but it was closer than the universe had ever been. Over millions of years, self-replicating molecules became enclosed in membranes, creating the first primitive cells. These tiny islands of order floated in oceans of entropy, small rebellions against disorder. And the universe, still unaware, had accidentally learned a new trick: persistence. With persistence came competition. With competition came evolution. And with evolution came complexity. Life did not begin with purpose. It began with chemistry that happened to outlast its rivals. And yet, out of this blind, indifferent process, something remarkable emerged. Organisms capable of adaptation, sensation, cooperation. Single cells became colonies. Colonies became simple animals. Simple animals became complex creatures with nervous systems. Biological circuits that could feel motion, warmth, danger. These early sensations were not thoughts. They were reactions, but reactions laid the groundwork for awareness. Awareness laid the groundwork for consciousness. Every step was incremental, built on the successes and failures of billions of tiny experiments conducted across millions of years. In time, nervous systems expanded, cells specialized, behaviors diversified. Animals began to navigate not only the environment but each other, developing memory, emotion, and increasingly sophisticated forms of perception. Eyes evolved, allowing organisms to capture light, the same light that had once illuminated the birth of galaxies. Ears evolved to detect waves traveling through air and water. Skin evolved to sense pressure, temperature, pain. Life grew not only more complex, but more curious. The universe, still silent, was teaching its creations how to listen. Somewhere along this grand ascent stood an ape-like species, fragile compared to predators, slow compared to prey, but equipped with a developing brain that grew not only in size but in capability. These early humans were not yet philosophers, but they were watchers, creatures who gazed at the night sky with something deeper than fear. They did not understand the stars, yet they felt drawn to them. The cosmos had placed inside their neural circuits the faintest spark of wonder. And wonder, once ignited, is a force evolution cannot easily extinguish. This brain, 3 pounds of neural tissue, would eventually become the most complex structure known in the universe, a structure capable of forming maps of reality inside itself, a structure capable of remembering the past, imagining the future, dreaming worlds that never existed, a structure capable of storytelling, science, and self-doubt. Consciousness was not merely an evolutionary advantage, it was a turning point. It allowed the universe to do something unprecedented, reflect. But consciousness is more than awareness. It is the capacity to ask questions no other creature asks. Questions like, what am I? Why am I here? How did all of this begin? Consciousness is curiosity turned inward. It is the moment the universe stops simply existing and begins to examine its own existence. And in humans, this examination reached a profound peak. The question of why there is something rather than nothing. This question is not practical. It is not necessary for survival. Yet it arises naturally from the depths of the human mind, as if the cosmos encoded its own origin story into the neurons of the beings it produced. But how did awareness arise from matter? How did neurons, electrochemical switches, give rise to thought, emotion, imagination? The answer remains elusive. Some theories suggest consciousness is an emergent phenomenon, the collective behavior of billions of neurons interacting. Others propose deeper roots, quantum processes within the brain, or information patterns that transcend biology. Whatever the mechanism, one truth is unshakable. Consciousness is built entirely from atoms forged in stars. The same atoms that once drifted through nebulae now form questions, memories, fears, hopes. The universe did not merely create stars, it created a way for those stars to be understood. This realization brings humility, for consciousness is both vast and fragile. It can contemplate galaxies, yet it depends on delicate networks of synapses. It can imagine eternity, yet it flickers in a finite lifespan. It can ask about the origins of reality, yet it remains confined to a small world orbiting a small star in a small corner of an ordinary galaxy. And still, despite this narrow vantage point, consciousness dares to explore the cosmos with mathematics, logic, imagination. Tools that allow humans to reach far beyond their physical limits. With the emergence of consciousness, the universe gained something it had never possessed. Meaning. Not objective meaning, imposed from outside, but subjective meaning generated within. Meaning is not inherent in the atoms of a star, but it is inherent in the minds that observe stars. Consciousness weaves narrative where none existed. It creates purpose where only physics ruled, and in doing so, it bridges the gap between the cold machinery of the cosmos and the warmth of lived experience. Through consciousness, the universe began telling stories about itself. At first around fires, then on cave walls, then through poetry, philosophy, and eventually science. These stories are not merely entertainment. They are attempts to reconcile our existence with the vastness that surrounds us. When humans map the stars, they are mapping themselves. When they measure cosmic expansion, they are measuring the scope of their own curiosity. When they search for the origin of everything, they are searching for their own origin. The universe has become both subject and observer. But something deeper lies within the human mind, the capacity to imagine nothingness. No other creature contemplates the void. No other species constructs philosophies around absence, non-existence, the before of all things. Humans alone return to that ancient question again and again, as if compelled by forces older than memory. Why is there something rather than nothing? Why did the universe choose existence? Why does consciousness find itself awake in a cosmos that could so easily have remained silent? This question is more than curiosity. It is a mirror. It reflects our longing for place, for purpose, for understanding. It reveals the tension between our smallness and our capacity for infinite thought. And it draws a profound circle around the entire cosmic story. From nothingness to somethingness to awareness of both. Consciousness is not merely the latest chapter. It is a return to the beginning, seen through new eyes. As humanity advances, so does its consciousness. Technology extends our senses. Telescopes expand our reach. Mathematics sharpens our understanding. We peer back billions of years to the earliest light. We detect gravitational waves from black hole collisions. We simulate universes inside machines built from silicon, elements once forged in ancient stars. Consciousness is the pathway through which the universe continues to explore itself. It is the mechanism by which cosmic history becomes more than a sequence of events. It becomes a story. And yet consciousness also brings vulnerability. To be aware is to feel. To feel is to suffer. To suffer is to recognize the fragility of existence. The stars do not worry about their death. The galaxies feel no grief, but conscious beings do. They understand loss. They understand time. They understand the weight of impermanence. Awareness opens the door to awe, but also fear. And still, consciousness persists because the ability to know outweighs the burden of knowing. In the end, consciousness is the rarest phenomenon in the cosmos. It is the spark that transforms matter into meaning. It is the bridge between what is and what is understood. It is the quiet observer standing at the edge of the infinite, asking questions that echo across space and time. The universe, once empty, now had eyes to look back at itself. From the first moment we asked what came before the universe, we stepped into a maze with no clear entrance and no clear exit. A question that seems simple, almost childlike, turns out to be one of the deepest puzzles the human mind can entertain. After journeying through epochs of creation, from quantum tremors to conscious thought, we return now to the beginning, or rather, to the absence of beginning, to the idea of nothing. And as we look back with everything we've learned, we find that nothingness, once feared as a void, now feels far more mysterious than we ever imagined, perhaps even impossible. Because the deeper we study the universe, the more it resists the notion of ever having been truly empty. Every time we think we've arrived at nothing, we find something hiding beneath it. Every time we strip away structure, a new layer of structure appears. Nothing continually dissolves in our hands. Physics gave us our first clues. What appears to be empty space is filled with fields, quantum fields that fluctuate, vibrate, and spawn particles from momentary blips of energy. Even the quietest vacuum is a storm in slow motion. But if a vacuum full of virtual particles is not nothing, we can go further. Could the absence of particles, fields, and forces be nothing? No, because even then, mathematical rules remain to describe the absence. Remove the rules, and still deeper truths lurk beneath. Symmetry principles, logical structures, potential frameworks for space-time. Remove those, and the very concept of removal becomes undefined. Nothing recedes as we approach it. Like a horizon, we can chase but never reach. What we call nothing becomes not an absence but a boundary, a limit to our understanding. Modern cosmology complicates the picture even further. Some propose a multiverse, a vast ensemble of universes bubbling endlessly in an ocean of inflating space. In such a scenario, our universe is just one bubble among countless others, each with its own laws, constants, and forms of matter. If this is true, then the question, why does our universe exist, becomes part of a broader, more bewildering inquiry. Why does inflation never stop? In some models, inflation is eternal, a process that produces universes as naturally as a tree produces leaves. If universes are constantly forming, then our existence is not surprising. What is surprising is that we ever expected nothingness to be the default at all. The multiverse reframes the entire mystery. Existence might be inevitable, while non-existence might be impossible. Other theories propose cyclical universes, cosmoses that expand, contract, collapse, and rebound endlessly. In this view, the Big Bang was not a beginning, but a transition, a bridge between an earlier universe and our own, a collapse giving way to a rebirth. If time stretches infinitely in both directions, then nothingness never had a chance to appear. Something has always been happening. Something has always existed. The universe may be eternal, not in the sense of having lasted forever, but in the sense of never having begun. A story with no first chapter, a song with no starting note. There are theories even stranger than these. Some suggest the universe emerged from a quantum fluctuation within a larger, timeless reality, a spontaneous breach in a state of pure potential. But pure potential is not nothing. Potential is something. Some physicists argue that mathematics itself is the fundamental substrate of reality, that the universe exists because mathematical structures exist. But if math is eternal, then again, nothingness loses its footing. And deeper still lies the possibility that consciousness, rather than matter, is the foundation of reality. In some interpretations of quantum mechanics, the act of observation shapes the world. But if observation is fundamental, if awareness plays a role in existence, then the universe cannot be purely physical, and nothingness becomes even more elusive. Every answer we propose points to a new question. Every layer we peel back reveals another. This infinite regress is not a failure of understanding. It is the very terrain of the mystery. Scientists, philosophers, and mystics all converge on a single insight. Nothingness, in the absolute sense, may simply not exist, not because the universe refuses to become empty, but because emptiness itself may be a flawed idea. Nothingness might be a mental construct, a shadow cast by the limitations of a consciousness built to navigate a world of objects and events. When the mind tries to imagine nothing, it uses the tools of something. Thought itself is a structure, incapable of representing its own absence. We are creatures of form, trying to grasp formlessness. And so, nothingness slips through our fingers, not because it is distant, but because it is incoherent. We can see this tension in the very way the universe behaves. Physics shows that the lowest energy state of the vacuum is not empty, that the laws of nature cannot be removed without creating new forms of structure, that even randomness carries a pattern, that even chaos follows rules. This suggests something profound. Maybe reality is not a layered cake with something on top and nothing at the bottom. Maybe reality is a spectrum of states, all of which are forms of something. Perhaps what we call nothing is simply a state of minimal structure, structure so subtle we mistake it for absence. But absence itself may have never existed at all. And if nothingness is impossible, then the universe does not need a cause in the way we expect causes operate within time. But time itself began with the universe. Asking what caused time is like asking what lies north of the North Pole. The question confuses the framework. The universe may be self-existing, not dependent on an outside trigger, not born from a void, not summoned by a prior state. It exists because existence is the simplest stable condition, or because non-existence is unstable, or because reality is a closed loop defining its own origins through laws we have not yet understood. We search for beginnings because our minds evolved in a world where every event has a cause. But the universe is not obligated to conform to the instincts of primates on a small blue planet. This brings us to a striking possibility. Nothingness may be an illusion created by the mind's attempt to simplify what it cannot fully grasp. Just as ancient people imagined edges to the earth because infinity was too overwhelming, perhaps we imagine the possibility of a universe emerging from nothing because true eternity, true self-existence, is too vast to hold. Nothingness feels intuitive only because our thoughts need contrast. We understand something by imagining its opposite. But opposites are tools of language, not necessarily features of reality. Perhaps the universe never faced a choice between something and nothing. Perhaps existence was always the default state, not because it is obvious, but because it is inevitable. Even the idea of before the universe dissolves under scrutiny. Time cannot precede the conditions that allow time to exist. Asking what happened before the Big Bang is like asking what happens before numbers begin. The framework itself has not yet been established. And if time is not fundamental, if it emerges from deeper laws or entanglements, then the very notion of nothingness existing before the universe collapses. There is no before. There is only the unfolding of something that was always capable of unfolding. And so we reach a strange humility. After exploring the edges of physics, the depths of cosmology, the spirals of galaxies, the emergence of life, and the dawn of consciousness, we return to the starting point, transformed. We set out asking, why is this something rather than nothing? But perhaps the real mystery is why we ever assumed nothing was an option. Maybe reality, in all its forms, energy, fields, mathematics, awareness, simply cannot reduce itself to absolute emptiness. Maybe nothing is the anomaly. not something. Maybe the universe is not a miracle emerging from a void, but a natural expression of deeper principles we have barely begun to touch. The cosmos does not answer these questions. It offers no reassurance. It only expands, reveals, transforms, and in its vast silence, we are left to confront a possibility both unsettling and beautiful. Nothingness may be the one thing the universe has never known. Maybe nothing never existed, and that is the greatest mystery of all. We end where we began, standing before the paradox that first set the universe in motion. We came seeking the meaning of nothingness, imagining it as a void, a silence, an absence from which all things somehow emerged. But the journey reshaped us. Nothingness, we discovered, is never truly empty. It is a mask, worn by laws we do not yet understand, a shadow cast by realities deeper than language, deeper than thought. And yet, from this almost nothing, something rose, something fragile, something improbable, something capable of becoming stars and galaxies, oceans and planets, minds and questions. Every atom within us was forged in the heart of a star that existed long before our world was born. Every thought we have arises from matter shaped by forces older than time as we know it. We are not separate from the paradox. We are its expression, its continuation, its unfolding. The universe did not choose us, but it made us possible, and in becoming aware, we became its witness. Perhaps nothingness was never real in the way we imagined. Perhaps the universe did not emerge from absence, but from a form of presence so subtle, so foundational, that we mistake it for nothing at all. Or perhaps the truth lies beyond all our metaphors, a mystery not meant to be solved, only approached. What we do know is this: everything we are exists because reality leaned toward being rather than not being, toward structure rather than emptiness, toward light rather than silence. And that single tilt shaped every moment that followed. In the end, nothing is not the opposite of everything. It is the doorway through which everything became possible.